Picture the final moments of a star, not just any star, but one so massive, so powerful, it dwarfs our Sun by millions of times. In its last act, it doesn't fade quietly. It erupts in a cataclysmic explosion, a supernova so brilliant it outshines entire galaxies for a fleeting moment. But here's the astonishing part. What's left behind isn't just scattered stardust. It's a time capsule, a celestial vault locking away secrets older than Earth itself. These remnants, neutron stars, black holes, swirling nebulae, are more than cosmic debris. They're the universe's way of preserving its own history, etching stories of creation, destruction, and rebirth into the fabric of space and time. Think about that for a second. Every atom in your body, every element that makes up our planet, even the gold in your jewelry, it all traces back to the heart of a dying star. These collapsing giants are the alchemists of the cosmos, forging the building blocks of life in their final, fiery breaths. But they're also historians. Hidden within their remnants are clues to how galaxies formed, how matter behaves under extreme conditions, and perhaps even how the universe itself might end. It's as if each supernova leaves behind a message in a bottle, waiting for us to decode it, and that's exactly what we're going to do today. We're embarking on a journey across space and time, peeling back the layers of these stellar graveyards to uncover what they can teach us. From the mind-bending physics of neutron stars where a teaspoon of material weighs as much as a mountain, to the eerie silence of black holes, we'll explore how these cosmic relics shape our understanding of everything. This isn't just about distant objects in the sky, it's about piecing together the story of us, because every time we gaze at the remnants of a dead star, we're looking back at our own origins, written in the language of light and gravity. So buckle up. By the end of this, you'll never look at the night sky the same way again. To understand how stars become cosmic time capsules, we need to follow their extraordinary journey from birth to death. Imagine a vast cloud of gas and dust floating silently in space, a stellar nursery where gravity slowly works its magic. Over millions of years, pockets of this cloud collapse under their own weight, heating up until nuclear fusion ignites in their cores. That spark marks the birth of a star, a furnace where hydrogen atoms fuse into helium, releasing the energy that makes stars shine. But not all stars live the same way or die the same way. A star like our Sun will burn steadily for billions of years before swelling into a red giant and eventually fading into a dense, Earth-sized ember called a white dwarf. Yet the real drama unfolds with the giant stars many times more massive than our Sun. These titans burn through their fuel at a furious pace, living fast and dying young in spectacular fashion. When they run out of fuel, their cores collapse in an instant, triggering an explosion so violent it can outshine an entire galaxy. This is a supernova, nature's ultimate fireworks display. What happens next is even more astonishing. The explosion flings the star's outer layers into space at incredible speeds, scattering heavy elements like iron, gold, and uranium across the cosmos. These elements don't just vanish, they become the raw materials for new planets, moons, and even life itself. Meanwhile, the core of the star undergoes a bizarre transformation. If it's dense enough, it crushes itself into a neutron star, an object so compact that a sugar cube-sized chunk would weigh as much as Mount Everest. Spin one of these ultra-dense remnants fast enough, and it becomes a pulsar, beaming radiation like a lighthouse across the galaxy. And if the core is even more massive, it collapses into a black hole, a gravitational trap so powerful not even light can escape. These remnants aren't just leftovers, they're cosmic record keepers. Neutron stars preserve details about the extreme physics of their creation, from the strength of their magnetic fields to the strange behavior of matter crushed beyond recognition. Black holes, though seemingly silent, warp space-time around them in ways that reveal the rules of gravity under the most extreme conditions. By studying them, we're not just learning about dead stars, we're uncovering the universe's hidden history, written in the language of gravity, light, and elemental dust. Every explosion, every remnant is a chapter in a story much bigger than any single star, and we're just beginning to read it. The sheer violence of a supernova is almost impossible to comprehend. In less than a second, a dying star releases more energy than our Sun will over its entire 10 billion-year lifetime. The shockwave tears through space at millions of kilometers per hour, heating surrounding gas to blistering temperatures and triggering waves of star formation in its wake. But this isn't just destruction, it's creation. The incredible forces at work inside the explosion act like a cosmic forge, smashing atoms together with such intensity that entirely new elements are born. Gold, platinum, uranium, the heavy metals we mine from Earth's crust were all cooked up in these fleeting, universe-shaking blasts. What makes supernova truly special isn't just their power, but their precision. The explosion unfolds in carefully orchestrated layers. As the star's core collapses, temperatures soar high enough to fuse lighter elements into heavier ones in rapid succession. Oxygen becomes silicon, silicon becomes iron, and in the final chaotic moments, the shockwave ripping outward from the core's collapse hurls these newly forged elements into the void. This isn't random scattering, it's a calculated distribution. The lightest elements travel farthest, while heavier metals like iron and nickel tend to stay closer to the explosion's epicenter. Scientists can actually map these patterns in ancient supernova remnants, reading them like cosmic fingerprints to reconstruct the star's final moments. And then there's the aftermath. The glowing debris field left behind isn't just a graveyard, it's a laboratory. Take the Crab Nebula, the scattered remains of a supernova observed from Earth in the year 1054. Even today, nearly 1,000 years later, its expanding cloud of gas still crackles with energy, powered by a spinning neutron star at its heart. By studying how these remnants evolve over centuries, we've uncovered clues about how shockwaves interact with interstellar gas, how magnetic fields shape stellar debris, and even how cosmic rays high-energy particles bombarding Earth from space are accelerated to near-light speed by these explosions. Perhaps most remarkably, supernovae serve as cosmic mile markers. Because these explosions follow predictable physics, they always peak at roughly the same brightness. That makes them perfect standard candles celestial beacons astronomers use to measure vast distances across the universe. By comparing a supernova's observed brightness to its known intrinsic brightness, we can calculate how far away it is with extraordinary precision. This technique helped reveal the shocking truth that our universe isn't just expanding, it's accelerating, driven by some mysterious force we now call dark energy. So every time a supernova flares in the distant cosmos, it's not just a dying star's last gasp, it's a message carrying secrets about the structure and fate of everything we know. Neutron stars are nature's ultimate paradox, cosmic objects so extreme they defy common sense. Picture squeezing the mass of our Sun into a sphere no wider than Manhattan. The result is a neutron star, where matter is compressed to such insane densities that protons and electrons fuse into neutrons, creating a substance unlike anything on Earth. A single sugar cube of this material would weigh more than all the cars, buildings, and people in a major city combined. Yet despite their unimaginable heft, neutron stars spin at dizzying speeds, some rotating hundreds of times per second. What makes these objects even more fascinating is how they interact with the universe around them. Many neutron stars emit intense beams of radiation from their magnetic poles. As they spin, these beams sweep across space like a lighthouse, appearing to pulse when viewed from Earth, earning them the name pulsars. These cosmic beacons are so precise that some rival atomic clocks in their regularity, ticking with near-perfect rhythm over decades. The first pulsar discovered, back in 1967, was initially nicknamed LGM-1, short for Little Green Men, because its unnaturally steady signals had scientists briefly considering an artificial origin. But the real magic of neutron stars lies in their ability to stretch the laws of physics to the breaking point. Their surfaces are so dense that if you dropped a marshmallow onto one from just a meter above, it would hit with the energy of a nuclear bomb. Their gravity warps space-time so severely that light bending around them creates bizarre optical illusions, and their magnetic fields, they're millions of times stronger than anything we've ever produced in labs, capable of ripping apart atoms from thousands of kilometers away. These extreme properties make neutron stars perfect natural laboratories. By studying them, scientists can test theories about how matter behaves under conditions so harsh they can't be replicated on Earth. For instance, the outer crust of a neutron star is likely a crystalline lattice of atomic nuclei swimming in a sea of electrons, while deeper layers might contain exotic states of matter like superfluids or even nuclear pasta, structures so strange they've been named after their spaghetti-like shapes. Some theories even suggest that the cores of the most massive neutron stars might harbor quark-gluon plasma, a primordial soup of particles that hasn't existed freely since the universe's first microseconds after the Big Bang. Beyond their sheer weirdness, neutron stars serve as cosmic timekeepers and historians. The oldest pulsars, spinning quietly in the depths of space, carry imprints of the universe's youth. By measuring tiny changes in their rotations, astronomers can detect gravitational waves rippling through space-time from collisions between black holes billions of light-years away. Others, locked in tight orbits with companion stars, allow us to test Einstein's theory of relativity with precision unmatched by Earth-bound experiments. Every flicker, every wobble in their rhythm tells a story about the star that died to create them, the forces shaping our universe, and perhaps even the ultimate fate of matter itself. So while black holes often steal the spotlight, neutron stars are the universe's unsung extreme athletes pushing the limits of physics, illuminating the darkest corners of space, and offering us front-row seats to phenomena we're only beginning to understand. They're not just remnants of stellar death, they're keys to unlocking some of the cosmos' most enduring mysteries. Pulsars are the universe's most meticulous timekeepers, spinning with such precision they make Swiss watches look crude by comparison. Born from the fiery death throes of massive stars, these neutron stars don't just fade into obscurity, they announce their presence with rhythmic pulses of radiation, flashing like cosmic lighthouses across the galaxy. What's astonishing isn't just their regularity, but how we've learned to harness it. Some pulsars spin hundreds of times per second, their beams sweeping past Earth with timing so exact, scientists can detect deviations as tiny as a millionth of a second. This isn't just a curiosity, it's a tool. When NASA Voyager spacecraft carried golden records into interstellar space, they included a pulsar map, a celestial GPS using these flashing beacons to pinpoint Earth's location for any hypothetical extraterrestrial finders. But pulsars do more than just keep time, they test the very fabric of reality. Einstein's theory of general relativity predicts how massive objects warp space-time, and pulsars provide the perfect laboratory to prove it. Take the famous Hulse-Taylor binary system, where two pulsars orbit each other in a dizzying dance. Over decades, astronomers have watched their orbits slowly decay, exactly matching Einstein's predictions about energy lost to gravitational waves. It's like watching a slow-motion ripple in space-time itself, with pulsars as the ultimate witnesses. What's equally remarkable is how pulsars preserve the story of their violent birth. The speed of a pulsar's spin, the tilt of its magnetic axis, even the faintest wobble in its rhythm, all these carry fingerprints of the supernova explosion that created it. Some pulsars rocket through space at over 1,000 kilometers per second, kicked by asymmetrical forces during their parent star's collapse. Others, like the pulsar at the heart of the Crab Nebula, still power their surrounding debris with relentless energy, a testament to the raw power unleashed when a star dies. For astronomers, pulsars are more than distant curiosities, they're workhorses. Arrays of radio telescopes can use their steady pulses to detect gravitational waves rolling across the galaxy, turning entire networks of pulsars into galaxy-sized detectors. Space agencies have even experimented with using them as natural navigation beacons for future interstellar missions, a celestial version of GPS that could guide ships between the stars. Every pulse carries information about the star's composition, the strength of its magnetic field, even the density of interstellar gas it's traveling through. Yet for all their precision, pulsars aren't immortal. Over millions of years, their spins gradually slow, their beams grow faint, and they eventually vanish into the darkness. But until then, they serve as both historians and pioneers, preserving the secrets of their explosive origins while helping us unravel the universe's deepest mysteries. Whether probing the nature of gravity, mapping the galaxy, or guiding future explorers, these cosmic clocks remind us that even in death, stars continue to light the way forward. Black holes aren't just cosmic vacuum cleaners, they're the universe's most secure vaults, locking away secrets in a gravitational grip so fierce even time itself bends to their will. When a star many times more massive than our Sun exhausts its fuel, its core doesn't just collapse, it implodes with such force that space and time warp around it, creating a boundary called the event horizon. Cross that invisible line and there's no turning back, but here's the twist. While black holes famously erase what falls in, they also leave behind cryptic clues about their origins. The star's mass, its spin, even the chaotic details of its death, all of it gets imprinted onto the black hole's shadowy surface like a cosmic fingerprint. Think of it like a burned book. From the outside, you might assume all the pages are lost forever, but in reality, the ashes still hold traces of the ink patterns waiting to be reconstructed. Similarly, a black hole's event horizon isn't just a one-way street. It's a dynamic, rippling surface that encodes information in ways we're only beginning to decipher. This idea, known as the holographic principle, suggests that everything swallowed by a black hole might leave a two-dimensional imprint on its boundary, like a projection on a giant celestial screen. It's as if the universe refuses to let information truly disappear, no matter how extreme the conditions. What makes black holes even more fascinating is how they challenge the very laws of physics. Take Hawking radiation, the faint glow predicted to seep from their edges. Over unimaginable timescales, this slow leak could cause black holes to evaporate entirely, raising a paradox about what happens to all that swallowed information. Does it vanish? Is it scrambled and released? Or does it linger, hidden in some quantum code we haven't cracked yet? These questions aren't just philosophical. They're rewriting our understanding of reality, forcing scientists to bridge the gap between Einstein's theory of relativity and the bizarre rules of quantum mechanics. Yet for all their mystery, black holes are far from silent. When two of them collide, they send ripples through space-time itself, gravitational waves that detectors like LIGO can now pick up from billions of light-years away. Each collision is like a cosmic drumbeat, revealing the black hole's masses, spins, and even hints about how they formed. Some might be remnants of ancient stars, while others could be primordial, born in the chaos of the early universe itself. And then there are the supermassive black holes lurking at the centers of galaxies, including our own Milky Way. These behemoths, weighing millions of suns, didn't just appear, they grew over eons, their feeding frenzies shaping entire galaxies around them. So while black holes might seem like the end of the story, they're really just another chapter. They're time capsules preserving the universe's most violent moments, laboratories testing physics at its limits, and even potential gateways through theoretical wormholes to other regions of space and time. Every discovery peels back another layer, showing us that these cosmic enigmas aren't just destructive forces. They're storytellers whispering clues about how stars live, die, and ultimately shape the cosmos we call home. Stellar archaeology turns the night sky into a cosmic dig site, where instead of shovels and brushes, astronomers use telescopes and spectrometers to sift through the ashes of dead stars. Imagine holding a prism to the light of a neutron star. As its glow fractures into a rainbow, dark lines appear like barcodes, each one revealing the star's chemical fingerprint. These spectral lines tell stories of nuclear fusion, of shock waves that forged gold and platinum, even of the star's final, cataclysmic moments. It's like translating hieroglyphs, but instead of ancient Egypt, we're deciphering the universe's earliest epochs. Take the oldest known stars in our galaxy, dim, metal-poor relics that formed when the universe was just a few 100 million years old. These ancient survivors are cosmic time capsules, their atmospheres preserving the pristine elemental mix of the early cosmos. Unlike younger stars polluted by generations of supernova debris, their composition mirrors the raw ingredients of the universe shortly after the Big Bang, mostly hydrogen and helium with traces of lithium. By studying them, we've uncovered clues about how the first stars, monsters hundreds of times more massive than our Sun, lived and died in spectacular explosions that seeded the cosmos with heavier elements. But stellar archaeology isn't just about reading individual stars. It's about reconstructing galactic history like piecing together a billion-year jigsaw puzzle. When a supernova detonates, it doesn't just vanish. Its shockwave carves bubbles in interstellar gas. Its ejected metals mix with surrounding clouds, and over eons, these enriched materials become part of new stars. By mapping the distribution of elements across the Milky Way, astronomers can trace these chemical footprints like breadcrumbs, revealing waves of star formation, collisions with dwarf galaxies, even the ghostly imprints of long-vanished stellar nurseries. One of the most remarkable discoveries came from studying rare elements like europium and uranium in ancient stars. Their proportions match predictions of neutron star mergers, violent collisions that shower space with heavy elements in a process called rapid neutron capture. This means the gold in your jewelry likely didn't come from a supernova, but from two dead stars spiraling together in a dazzling kilonova explosion billions of years ago. It's a revelation that rewrote our understanding of cosmic alchemy, showing how stellar archaeology can solve mysteries even its practitioners didn't expect. The field keeps pushing boundaries. Some teams now analyze starlight for isotopic ratios, variations in atomic nuclei that act like stopwatches, timing how quickly elements were forged in ancient stellar explosions. Others hunt for hypervelocity stars, ejected from the galactic center by the supermassive black hole's gravity. their trajectories encoding clues about the Milky Way's turbulent past. And with next-generation telescopes like the James Webb Space Telescope peering deeper into the infrared, we're starting to uncover population Roman 3 stars, the mythical first generation born from pure Big Bang material, whose existence until now was only theoretical. What makes stellar archaeology so powerful is its ability to turn faint starlight into a time machine. Every photon carries information about temperatures, pressures, velocities, even the magnetic fields that shaped a star's death throes. By collecting enough of these cosmic whispers, we're not just studying dead stars, we're assembling a grand narrative, one that stretches from the universe's fiery birth to the delicate chemistry that made life possible. And with every new observation, we add another paragraph to the story written in the stars themselves. The universe has a secret recipe for creating gold, platinum, and other heavy elements, and it doesn't involve ordinary stars. While most stars spend their lives fusing hydrogen into helium and eventually carbon or oxygen, the process stops at iron. Fusing iron actually absorbs energy instead of releasing it, like trying to start a fire with wet wood. So where do all the heavier elements come from? The answer lies in the most violent events in the cosmos: supernova explosions and the spectacular collisions of neutron stars. When a massive star goes supernova, the sheer force of its collapse creates a fleeting environment hotter and denser than the star's core. In this extreme crucible, atomic nuclei are bombarded by a flood of free neutrons, allowing them to rapidly capture these particles and build heavier elements in a process called the Rapid Neutron Capture Process, or R process. This is how elements like uranium, gold, and platinum are forged not in the steady burn of a star's lifetime, but in the chaotic final seconds of its death. But supernova aren't the only cosmic foundries. Neutron star mergers when two of these ultra-dense remnants spiral together and collide, unleash even more intense conditions. The resulting kilonova explosion is so rich in neutrons that it can produce staggering amounts of heavy elements in mere seconds. In fact, a single neutron star collision might manufacture hundreds of Earth masses worth of gold and platinum, scattering them across space in glowing, radioactive debris. These precious metals don't just vanish into the void. Over millions of years, they mix with interstellar gas and dust, eventually becoming part of new generations of stars and planets. That means the gold in your ring or the uranium in nuclear reactors was once stardust, forged in a cataclysm that occurred long before our solar system existed. It's a humbling thought. Every heavy element on Earth carries the legacy of ancient stellar explosions. Scientists can even track this cosmic recycling program by studying the chemical makeup of stars across our galaxy. Younger stars, like our Sun, contain higher concentrations of these heavy elements because they formed from gas enriched by countless supernova and mergers. Older stars, born when the universe was still metal-poor, carry barely a trace. By mapping these differences, astronomers can reconstruct a timeline of stellar deaths, like detectives piecing together a crime scene from scattered evidence. One of the most fascinating discoveries came from the collision of two neutron stars observed in 2017. The event, dubbed GW170817, wasn't just detected through gravitational waves. Telescopes also caught the glow of newly created heavy elements in the aftermath. The data revealed signatures of gold, platinum, and other R-process elements, confirming what theorists had long suspected. These dazzling cosmic crashes are among the universe's primary jewelry stores. So the next time you look at the night sky, remember those twinkling stars aren't just distant suns. They're the descendants of explosions that sprinkled the cosmos with the very elements that make up our bodies, our technology, and our world. Every heavy atom is a time capsule, a silent witness to the violent, beautiful processes that built everything we know. Every atom in your body, every rock on Earth, even the air we breathe, it all traces back to the explosive deaths of stars that shone billions of years before our solar system existed. This isn't poetic exaggeration, it's the universe's grand recycling program in action. When a massive star ends its life in a supernova, it doesn't just leave behind a remnant, it scatters its guts across light years of space, seeding the cosmos with the ingredients for new worlds. The iron in your blood, the calcium in your bones, even the silicon in your smartphone, they were all forged in the heart of a dying star, then catapulted into the void by unimaginable forces. Picture a vast molecular cloud drifting through the galaxy, a cosmic junkyard filled with debris from countless stellar explosions. Over millions of years, gravity pulls these scattered elements together, compressing them until new stars ignite in their cores. But this time, something different happens. Because the cloud is laced with heavy elements from past supernova, the newborn stars aren't alone. Around them, flecks of dust rich in carbon, oxygen, and metals clump together, forming planets, asteroids, and eventually, given the right conditions, the building blocks of life. Our solar system was born in one such enriched cloud around 4.6 billion years ago, making Earth and everything on it a direct product of recycled stardust. The evidence is everywhere. Meteorites that crash to Earth contain microscopic grains older than the Sun itself, tiny time capsules preserving material from stars that died before our solar system formed. These presolar grains, as they're called, have isotopic signatures that match predictions of supernova nucleosynthesis, proving they were forged in stellar explosions. Some even contain stardust from red giants, stars that puffed away their outer layers gently rather than exploding. It's as if the universe left us a forensic trail, with each grain telling us exactly which type of star contributed to our cosmic ancestry. But the recycling doesn't stop at stardust. When stars like our Sun reach the end of their lives, they too return material to the galactic supply chain. A dying sun-sized star sheds its outer layers as a glowing planetary nebula, expelling carbon, nitrogen, and other life-essential elements back into space. These gentle giants don't explode with the violence of supernova, but their contributions are just as vital. Without them, the universe would lack the diversity of elements needed for complex chemistry, and by extension, life as we know it. This cycle of stellar death and rebirth isn't just a quirk of our galactic neighborhood, it's the driving force behind the universe's growing complexity. Early in cosmic history, only hydrogen and helium existed. But with each generation of stars, new elements were added to the mix, allowing richer chemistry and more varied planetary systems to emerge. Today, we see this evolution reflected in the metal content of stars across the Milky Way. Older stars, born when the universe was still pristine, contain almost no heavy elements. Younger stars like our Sun are metal-rich, beneficiaries of billions of years of stellar recycling, and future stars will inherit even more diverse materials, including elements created in neutron star mergers and other exotic events we're only beginning to understand. So when you gaze at the night sky, you're not just looking at distant points of light. You're seeing a cosmic assembly line, one where stars live die and transform their ashes into new generations of worlds. Every planet, every moon, every speck of interstellar dust is part of this unbroken chain, linking the universe's fiery beginnings to the delicate chemistry that makes our existence possible. The atoms in your hands right now have crossed billions of years and countless light years to be here, carrying with them the legacy of stars long gone. And one day, far in the future, those same atoms may find themselves part of new worlds, new life, or even new civilizations, continuing the cycle that turns stardust into stories. Deep within the crushing gravity of a neutron star's crust, atoms are packed so tightly they form a crystalline lattice unlike anything on Earth, a frozen snapshot of the star's violent birth. This isn't just dense matter, it's a cosmic hard drive preserving data about the supernova explosion that created it. The crust's thickness, its seismic vibrations, even the way it cracks under unimaginable pressure. All these details hold clues about the star's original mass, rotation speed, and the turbulent conditions of its death. Scientists call these features starquakes, and observing them is like listening to the echo of a cosmic explosion frozen in time. Black holes take this concept even further. According to the holographic principle, every bit of information swallowed by a black hole leaves a two-dimensional imprint on its event horizon, the point of no return. Think of it like a celestial fingerprint where the star's mass, spin, and charge are forever encoded in the way the horizon ripples and distorts. While we can't retrieve what's inside, these surface patterns act as a permanent record, a kind of cosmic etch-a sketch preserving the story of the star's collapse. It's as if the universe, determined not to lose its history, found a way to engrave it onto the very fabric of space itself. What makes these stellar relics so invaluable is their longevity. A neutron star's magnetic field, for instance, can remain virtually unchanged for millions of years, acting as a frozen compass needle pointing back to the star's explosive origins. Pulsars, spinning neutron stars that beam radiation like lighthouses, keep perfect time over eons, their steady pulses serving as cosmic chronometers. By measuring slight variations in their rhythms, astronomers can detect the subtle tug of passing gravitational waves or the ghostly pull of dark matter, turning these dead stars into some of the universe's most sensitive detectors. But perhaps the most astonishing time capsules are the elements forged in stellar explosions. Heavy metals like gold, uranium, and platinum don't just scatter randomly, their isotopic ratios carry timestamps. For example, the amount of radioactive uranium-238 left in a star's debris can tell us how long ago the supernova occurred, much like carbon dating ancient artifacts on Earth. Some neutron stars even trap exotic states of matter in their cores, superfluid neutrons or quark-gluon plasma, that haven't existed freely since the universe's first microseconds. Studying them is like cracking open a prehistoric amber seal, revealing conditions we can't recreate even in our most powerful particle colliders. The real magic happens when we piece together these clues. By comparing the spin rates of young neutron stars with older ones, we've reconstructed how stellar corpses slow down over cosmic time. Analyzing the distribution of elements in ancient star clusters has revealed waves of supernova that swept through our galaxy billions of years ago, seeding it with the materials for planets and life. Even black holes, seemingly the ultimate erasers of information, contribute to this cosmic archive. The gravitational waves they emit when colliding carry precise details about their masses and spins, allowing us to census populations of invisible stellar remnants across the universe. This isn't just astronomy, it's archaeology on a galactic scale. Every neutron star's vibration, every black hole's shadow, every speck of stardust is a page in a chronicle written long before Earth formed. And as our telescopes grow sharper, we're not just reading that history, we're learning how to decode the universe's deepest secrets, one collapsed star at a time. The collision of two neutron stars isn't just a visual spectacle, it's a cosmic symphony, sending ripples through the very fabric of space-time that echo across billions of light years. These gravitational waves, first predicted by Einstein over a century ago, aren't like sound or light. They're distortions in the universe's structure itself, stretching and squeezing everything in their path as they travel at the speed of light. When detectors like LIGO and Virgo catch these faint tremors, they're not just recording a crash, they're decoding a message etched into the geometry of reality, revealing details no telescope could ever see. Take the historic detection in 2017, when two neutron stars collided 130 million light-years away. The gravitational waves told scientists the stars' masses, each roughly 1.4 times heavier than our Sun, and their frenzied spin rates as they spiraled toward catastrophe. But the real treasure came in the aftermath. Seconds after the waves arrived, space telescopes caught a gamma-ray burst, followed by a glowing kilonova, proof that the collision had forged heavy elements like gold and platinum in quantities that dwarfed Earth's entire reserves. For the first time, humanity had witnessed both the gravitational and light signatures of the same cosmic event, opening a new era of multi-messenger astronomy. What makes gravitational waves so revolutionary is how they complement traditional observations. Light can be blocked by dust or distorted by gravity, but gravitational waves pass through everything unimpeded, carrying pristine information about their sources. The shape of the wave, how its frequency rises and falls, reveals whether the colliding objects are black holes, neutron stars, or something even stranger. The timing of when different detectors receive the signal pinpoints the event's location in the sky with astonishing precision, and subtle fingerprints in the waveform, like tidal distortions, hint at whether a neutron star was stretched apart before merging, offering clues about the mysterious state of matter in its core. These detections are also putting Einstein's theories to the ultimate test. General relativity predicts exactly how gravitational waves should behave, from their propagation speed to how they weaken with distance. So far, every observed wave has matched these predictions with uncanny accuracy, even in environments where gravity is billions of times stronger than anything in our solar system. But scientists are hunting for tiny deviations that might reveal cracks in relativity's foundation, potentially pointing toward new physics, like quantum gravity or hidden dimensions. Beyond testing theories, gravitational waves are rewriting the cosmic census. Before LIGO, no one knew how often neutron stars collide. Now, with dozens of mergers logged, patterns are emerging. Some neutron star pairs orbit so closely they'll merge in a few 100 million years, a blink in cosmic time. Others, like the bizarre object GW190421, might be the first detected mass gap collision, a mystery object too heavy to be a neutron star but too light to be a black hole. Each detection adds a piece to the puzzle of how stars live, die, and reshape the universe around them. The most thrilling part, we're just scratching the surface. Future detectors like space-based LISA or next-generation ground observatories will catch waves from supermassive black hole mergers, primordial cosmic strings, even echoes of the Big Bang itself. It's as if we've been given a stethoscope to listen to the universe's heartbeat, and with every new ripple, we're hearing stories older than the stars themselves. Deep in the hearts of neutron stars, where matter is crushed to unimaginable densities, scientists are searching for traces of something even more elusive: dark matter. This mysterious substance, which outweighs all visible matter in the universe 5-to-1, has never been directly detected. But what if the key to unlocking its secrets isn't in some distant galaxy or high-tech lab, but in the remnants of dead stars? Some theories suggest that as neutron stars form, their incredible gravity could act like cosmic flypaper, trapping dark matter particles that would otherwise zip through space unnoticed. Over time, these captured particles might accumulate in the star's core, subtly altering its temperature, rotation, or even how it collapses further. The idea hinges on a tantalizing possibility that dark matter doesn't just ignore ordinary matter entirely. While most models assume dark matter particles barely interact with anything, even a tiny fraction of them could get snagged by a neutron star's gravitational pull. Once inside, collisions with the star's ultra-dense neutrons might cause the dark matter to lose energy, sinking toward the core like sand settling in water. In some scenarios, this buildup could generate enough heat to slow the neutron star's cooling process, something astronomers might detect by comparing young and old stellar remnants. Other models propose more dramatic effects like dark matter catalyzing the star's collapse into a black hole far sooner than predicted. These hypotheses aren't just speculative, they're testable. Take the case of a neutron star called Hess J 1731-347. Observations suggest it's far cooler than its age should allow, as if something is insulating its core. Could dark matter be the culprit, or consider pulsars that suddenly glitch, their usually precise spins hiccuping without explanation? While most glitches are attributed to starquakes or superfluid vortices, a few theorists wonder if dark matter interactions could play a role, like invisible grit in a cosmic gearbox. Even black holes might hold clues. If dark matter indeed alters neutron star evolution, we'd expect fewer mid-mass black holes in regions dense with dark matter, a pattern telescopes are now hunting for. What makes this search so revolutionary is how it flips the script. Instead of building bigger detectors to catch dark matter on Earth, we're using neutron stars as ready-made laboratories, their extreme gravity doing the heavy lifting. It's like turning the entire galaxy into a dark matter telescope, and the implications stretch beyond astrophysics. If dark matter truly leaves fingerprints in these stellar corpses, it could reveal whether the particles are cold, slow-moving, or warm, faster, how strongly they interact with normal matter, and even if they're part of a larger, hidden sector of particles outside our current physics models. So while dark matter remains invisible, its cosmic dance with dying stars might finally bring it into the light. Every neutron star could be more than a relic. It might be a Rosetta Stone waiting to translate the universe's darkest secret. And as we peer into these ultra-dense time capsules, we're not just studying stellar death, we're decoding the hidden architecture of reality itself. If advanced civilizations exist among the trillions of stars in our galaxy, why haven't we found a single trace of them? This is the heart of the Fermi paradox, the unsettling silence that greets us as we scan the cosmos for signs of intelligence. But what if we've been looking in the wrong places? Stellar remnants, those dense relics of dead stars, might hold the answer. Imagine a civilization so advanced, it treats neutron stars like cosmic flash drives, encoding information in their precise pulsations, or manipulating black holes into storing vast libraries within their warped space-time. Theoretically, a sufficiently advanced society could imprint messages in the spin rates of pulsars, creating patterns distinguishable from natural signals. A sequence of prime numbers buried in the timing, or an unmistakable modulation in the beam's intensity, would scream artificial to any listening civilization. Yet after decades of searching, our radio telescopes have detected no such signatures. This absence could mean one of two things. Either intelligent life is vanishingly rare, or it communicates in ways we're only beginning to imagine. Some scientists suggest that black holes might be the ultimate data vaults for advanced species. According to theoretical physics, information swallowed by a black hole isn't truly destroyed. It's scrambled and preserved on the event horizon's surface. A civilization capable of manipulating black holes could potentially encode data in their Hawking radiation, or even structure their mergers to emit deliberate gravitational wave patterns. These wouldn't be radio signals we'd recognize, but mathematical fingerprints hidden in the fabric of space-time itself. The eerie quiet might also hint at something darker, that intelligent life tends to self-destruct before reaching the technological stage required for such cosmic engineering. The same stellar remnants we study as time capsules could double as tombstones, marking where civilizations once harnessed their star's energy before collapsing under war, resource depletion, or environmental catastrophe. Or perhaps the answer is simpler. The universe is so vast that even if other civilizations are out there, their signals haven't reached us yet. Light and gravitational waves travel fast, but not infinitely fast. We might be listening for whispers from neighbors who vanished millions of years ago. But there's still reason to hope. As our observational tools grow sharper, we're uncovering subtler ways to search for extraterrestrial intelligence. Next-generation telescopes could analyze the spectra of exoplanet atmospheres for industrial pollutants, evidence of technology not meant for us to find. Gravitational wave detectors might one day catch engineered mergers where black holes collide with unnatural precision. Even the strange dimming of stars, once attributed to dust clouds, could theoretically be caused by massive alien megastructures harvesting energy. The truth is, stellar remnants offer more than just a window into the universe's past. They could be the billboards of advanced civilizations, broadcasting their existence across eons. Whether we'll find those messages depends on how creatively we look and whether anyone out there is trying to be found. Until then, the silent corpses of dead stars keep their secrets, leaving us to wonder if we're the first to ask these questions, or merely the latest in a long line of cosmic archaeologists sifting through the ashes of a galaxy that's far stranger than we've dared to imagine. Neutron stars are nature's most extreme physics experiments, squeezing matter into forms so bizarre they defy our understanding of reality. At their cores, pressures reach levels so intense that atomic nuclei cease to exist, crushed into a soup of quarks and gluons, the fundamental building blocks of protons and neutrons. This quark-gluon plasma hasn't existed freely since the universe's first microseconds after the Big Bang, yet inside neutron stars, it might persist like a fossilized echo of creation itself. Some theories go even further, suggesting that under these conditions, quarks could reorganize into strange matter, a stable, ultra-dense state where up and down quarks mix with their exotic cousin, the strange quark. If true, entire neutron stars could transform into strange stars, their cores becoming indestructible nuggets of this primordial substance. What makes these possibilities so revolutionary isn't just their weirdness, it's how they bridge the gap between quantum mechanics and Einstein's theory of gravity. Neutron stars are where the tiny world of particle physics collides with the vastness of spacetime curvature. In their cores, quantum effects like Pauli exclusion, the rule that prevents neutrons from occupying the same state battle against gravity's relentless crush. This balancing act creates environments where the rules of quantum physics are stretched to their limits, offering clues to how they might mesh with relativity. For instance, if quark matter in neutron stars exhibits properties like superfluidity flowing without friction, it could explain why some pulsars suddenly glitch, their spins hiccuping in ways that defy classical predictions. Scientists are racing to test these ideas with tools ranging from gravitational wave observatories to particle colliders. When neutron stars merge, the resulting gravitational waves carry subtle imprints of their internal structure, hinting at whether their cores are made of neutrons, free quarks, or something even stranger. Meanwhile, labs like CERN recreate microsecond glimpses of quark-gluon plasma by smashing heavy ions together at near light speed. By comparing these experiments to observations of neutron stars, researchers are piecing together a unified picture of matter across cosmic scales. The implications stretch far beyond astrophysics. If strange matter exists inside neutron stars, it could be stable enough to endure outside them, meaning any chunk of this material, if ejected during a collision, might convert ordinary matter it touches into more strange matter. While this strange-alert scenario remains speculative, it illustrates how neutron stars aren't just distant curiosities. They're cosmic probes testing the boundaries of what's possible, and in doing so, revealing secrets about the universe's birth, evolution, and perhaps even its ultimate fate. Every pulse from a neutron star, every ripple in spacetime from their collisions, is a coded message waiting to be translated. And with each breakthrough, we come closer to cracking the universe's deepest cipher. Black holes aren't just cosmic vacuum cleaners, they're the ultimate enforcers of a paradox that has physicists scratching their heads. When a dying star collapses into a black hole, every bit of matter and energy it swallows seems to vanish behind the event horizon, erased from the universe forever. But here's the catch: quantum mechanics insists that information, the detailed state of every particle, can never truly be destroyed. This contradiction, known as the black hole information paradox, has been keeping scientists awake at night for decades. At first glance, a black hole appears to be the perfect shredder. Toss in a book, and according to classical physics, not only is the book gone, but the information printed on its pages is irretrievably lost. Yet quantum mechanics operates under strict accounting rules. Every interaction, every collision between particles must be reversible in principle. That means if you knew the exact state of the universe right now, you could theoretically rewind time and reconstruct everything that ever happened. Black holes seem to break this rule, swallowing information without a trace. Enter Stephen Hawking's revolutionary insight. In the 1970s, he predicted that black holes aren't completely black, they slowly leak energy in the form of Hawking radiation. At first, this seemed to make the paradox worse. Hawking radiation is thermal, meaning it carries no information about what fell in. It's like burning that book and claiming the smoke particles contain its words. But recent breakthroughs suggest a way out. The event horizon, that one-way boundary around a black hole, might not be the featureless surface it appears to be. Instead, it could act like a scrambled hard drive, encoding swallowed information in quantum fluctuations so subtle we've only begun to understand them. Imagine the event horizon as a hall of mirrors, but instead of reflecting light, it reflects quantum states. As particles approach, their information gets smeared across the horizon's surface in a two-dimensional hologram, an idea known as the holographic principle. Later, when Hawking radiation escapes, it might carry away imprints of that scrambled data, like steam rising from a pot of alphabet soup still shaped by the letters at the bottom. The math suggests this process could preserve information without violating any laws, but proving it remains one of physics' greatest challenges. Why does this matter beyond theoretical puzzles? Because black holes are cosmic laboratories where gravity and quantum mechanics collide. Solving the information paradox could reveal how these two frameworks, which currently describe our universe in incompatible ways, actually fit together. It might even point toward the long-sought theory of quantum gravity, a single rulebook governing everything from the tiniest particles to the largest structures in the cosmos. The key to unlocking this mystery might lie in the remnants of collapsing stars. When neutron stars teeter on the brink of becoming black holes, their extreme conditions could mimic the quantum gravitational effects we're trying to understand. Gravitational waves from their collisions might carry subtle distortions that hint at how information behaves at the edge of oblivion. Every time we detect one of these cosmic crashes, we're not just watching stellar debris, we're peering into the universe's deepest code, searching for the line where destruction becomes preservation, and where the secrets of reality itself might be hiding in plain sight. Every second, trillions of invisible bullets rip through Earth's atmosphere. Cosmic rays, the high-energy shrapnel of dying stars. These aren't light waves or radio signals, but actual particles accelerated to nearly the speed of light by some of the most violent events in the cosmos. When a massive star explodes as a supernova, its shockwave doesn't just fling heavy elements into space. It acts like a natural particle accelerator, boosting protons and atomic nuclei to energies that dwarf anything we can create in human-built colliders. Some cosmic rays carry so much energy, a single particle packs the punch of a major league fastball, all condensed into something smaller than an atom. What makes these particles so valuable is their origin story. Unlike light, which can be scattered or absorbed on its journey, cosmic rays retain crucial details about where and how they were accelerated. By capturing them with ground-based detectors or high-altitude balloons, scientists can analyze their composition and energy like cosmic fingerprints. Some bear the signature of fresh supernova remnants, their chemical makeup matching the debris from recent stellar explosions. Others trace back to rapidly spinning neutron stars, where intense magnetic fields whip particles outward like a slingshot. A rare few may even come from beyond our galaxy, carrying whispers of cataclysms we've yet to discover. The journey these particles take is just as fascinating as their sources. Many cosmic rays travel for millions of years through interstellar space, zigzagging along magnetic fields until chance brings them to Earth. When they collide with our atmosphere, they create cascades of secondary particles, air showers that spread over kilometers, allowing detectors to reconstruct the original particle's energy and direction. This turns our entire planet into a giant cosmic ray telescope, with each detection adding another piece to the puzzle of how dead stars shape the universe around them. Perhaps most remarkably, cosmic rays connect us to processes we can't directly observe. The highest energy particles, dubbed "Oh my God" particles by astonished scientists, pack energies millions of times greater than anything produced in supernova. Their origins remain one of astrophysics' greatest mysteries, perhaps from active galactic nuclei, where supermassive black holes fling matter across space, or from collisions of entire galaxy clusters. Whatever their source, they prove that stellar corpses aren't just relics of the past. They're active engines, still shaping the cosmos by accelerating particles that eventually find their way to us, carrying encrypted messages about the universe's most extreme environments. By studying these energetic messengers, we're not just learning about dead stars, we're tracing the invisible highways of the galaxy, mapping how energy and matter circulate through space. Every cosmic ray that reaches Earth is a reminder that the universe speaks to us in countless ways, if only we know how to listen. The Crab Nebula isn't just a cloud of cosmic debris, it's a time-lapse photograph of stellar death unfolding in slow motion. Nearly 1,000 years after the supernova that birthed it lit up Earth's skies in 1054, this glowing remnant still pulses with energy, powered by the frenetic spin of a neutron star at its heart. Clocking in at 30 revolutions per second, this stellar corpse beams radiation into the surrounding gas like a lighthouse cutting through fog, illuminating intricate shockwaves and filaments that reveal the physics of the original explosion. What makes these stellar ghosts so valuable is how they evolve. In their earliest stages, remnants expand at staggering speeds, up to 30 million kilometers per hour, plowing into surrounding interstellar material and heating it to millions of degrees. This creates X-ray glows detectable by space telescopes, painting a vivid picture of how heavy elements like oxygen, neon, and iron mix with the interstellar medium. Over centuries, the expansion slows as the remnant interacts with more material, morphing from a ragged fireball into delicate, lace-like structures. The Veil Nebula, for example, shows this late-stage transformation, its wispy tendrils spanning over 100 light-years while still bearing the chemical fingerprints of the star that died millennia ago. But the real treasure lies in how these remnants remember their explosions. Take Cassiopeia A, the rubble from a supernova that likely occurred around 1680. Unlike the symmetrical debris fields textbooks often depict, this remnant is a chaotic jumble of knots and jets, betraying asymmetrical forces during the star's collapse. Iron-rich chunks hurtle outward in one direction, while silicon and sulfur blaze trails elsewhere, a cosmic autopsy showing how the dying star convulsed in its final moments. Even more telling are the light echoes, delayed reflections of the original explosion bouncing off interstellar dust clouds. By analyzing these faint optical ghosts, astronomers confirmed that Cas A's progenitor was a rare Type Ib supernova, a star that shed most of its hydrogen envelope before exploding. These glowing graveyards also serve as natural particle accelerators. As supernova shockwaves plow through space, they trap charged particles in magnetic fields, boosting them to near-light speed. This creates cosmic rays, high-energy protons and atomic nuclei that constantly bombard Earth. The remnants themselves become radio beacons, their synchrotron radiation betraying the presence of ultra-relativistic electrons spiraling around magnetic field lines. Some, like the bizarre object G0.9 plus 0.3 near our galaxy's center, even re-energize themselves by plowing into dense gas clouds, proving that stellar death isn't a one-time event but an ongoing process shaping galactic ecosystems. Perhaps most poetically, these remnants become stellar recycling plants. The Crab Nebula alone contains enough oxygen, carbon, and nitrogen to seed thousands of future planetary systems. Over millions of years, its filaments will disperse, blending with other clouds until gravity pulls them into new stars that might one day host planets with atmospheres made from atoms forged in that ancient cataclysm. So while we gaze at these glowing ruins as monuments to destruction, they're equally blueprints for creation, ensuring that even in death, stars never truly vanish. They simply transform, leaving behind shimmering roadmaps for anyone patient enough to read them. The universe keeps perfect records, even if it takes trillions of years to read them. Long after the last stars fade and galaxies drift apart, the remnants of collapsed stars will endure as silent archivists, holding onto secrets from an era when the cosmos crackled with light and heat. Neutron stars, those ultra-dense cinders of stellar giants, will gradually cool over millennia, their searing surfaces dimming as residual heat leaks into space. But their magnetic fields, imprinted at birth like cosmic birthmarks, will persist, preserving a frozen snapshot of the violent supernova that created them. These fading embers might one day be the only evidence that stars like our Sun ever existed at all. Black holes face an even stranger fate. According to Hawking radiation, these gravitational monsters aren't truly eternal. Slowly, imperceptibly, they'll leak energy, their event horizons shrinking like ice melting in reverse. For a typical stellar mass black hole, the process would take longer than the current age of the universe, but given enough time, even the mightiest will evaporate in a final burst of particles. Yet until that distant moment, every black hole remains a locked vault. The information scrambled across its surface, the mass, spin, and charge of everything it swallowed stays preserved like words etched on an indestructible plaque. Future astronomers might decode these signatures to reconstruct entire chapters of cosmic history, piecing together stories from epochs when the universe was young and crowded with stars. What's astonishing is how these relics could serve as teaching tools for civilizations unimaginably far in the future. Picture a society rising billions of years from now in a galaxy where new stars no longer form. With no active supernova to study, they might turn to neutron stars as their only window into stellar life cycles. By measuring the faint thermal glow of a cooled remnant, they could calculate its original mass. By mapping the subtle warping of space around ancient black holes, they might deduce the properties of long-vanished galaxies. These cosmic artifacts would become their textbooks, their museums, their connection to a universe far more vibrant than the one they inhabit. The ultimate irony, the very processes that erase these remnants also create new opportunities for discovery. As black holes evaporate, their final moments could release bursts of high-energy radiation, a last whisper of data before vanishing entirely. Some theories suggest this radiation might carry imprints of the black hole's history, like a final confession at the edge of oblivion, and neutron stars, even as they cool, could collide in slow-motion mergers, their gravitational waves echoing through an otherwise silent cosmos. For any civilization listening, these events would be like finding a message in a bottle floating on the tide of deep time. So while stars live fast and die young, their remnants inherit a different role, not as blazing beacons but as patient librarians. They'll outlast planets, outlast galaxies, perhaps even outlast life itself. But as long as they endure, they'll keep telling the same story. How a universe of chaos and fire gave rise to everything we know, and how even in death, the stars made sure we'd never forget. Pulsars might be the universe's most reliable postal service if we know how to send a letter. These spinning neutron stars beam radiation with such clockwork precision that their pulses rival atomic clocks on Earth. The idea of using them as cosmic lighthouses isn't science fiction, it's already in practice. When NASA launched the Voyager probes, they included pulsar maps on their golden records, a celestial address system pointing back to Earth using the unique signatures of 14 pulsars. Each one acts like a galactic mile marker, with its spin rate and direction forming a three-dimensional coordinate that any spacefaring civilization could decode. But navigation is just the beginning. The real intrigue lies in communication. A pulsar's pulses aren't just steady, they're programmable. By slightly modulating the timing or intensity of these beams, something far beyond our current technology, but theoretically possible for an advanced civilization, information could be embedded like Morse code in the flashes. Imagine a sequence of pulses deliberately spaced to spell out prime numbers or mathematical constants. Such patterns would stand out against nature's randomness, screaming, artificial to anyone listening. Scientists have even proposed that a sufficiently advanced society might hijack a pulsar's magnetic field, altering its spin to transmit data across thousands of light years. The flip side is equally tantalizing. If aliens use pulsars as signal beacons, we might already have their messages buried in decades of radio telescope data. Programs like SETI have traditionally hunted for intentional radio transmissions, but pulsar signals are omnidirectional and energy-efficient, perfect for a civilization wanting to broadcast widely without targeting specific stars. Some researchers suggest sifting through known pulsar data for anomalies, a skipped pulse, an irregular rhythm, or a frequency modulation that defies astrophysical explanation. The famous WOW signal, a one-off burst detected in 1977, remains unexplained. Could it have been a pulsar-based message we mistook for noise? What makes pulsars especially compelling as communication tools is their longevity. Unlike radio broadcasts that fade into static, a pulsar's signal persists for millions of years. A message encoded in its pulses would outlast the civilization that sent it, becoming a time capsule for future species. This raises eerie possibilities. The pulsars we observe today might already carry whispers from extinct civilizations, their final broadcasts echoing long after their senders vanished. Alternatively, they could be part of a galactic network, with each pulsar acting as a node in a relay system spanning the Milky Way. A message from one side of the galaxy could hop between pulsars, reaching destinations far beyond the limits of direct transmission. Yet the silence so far might hint at a darker reality. If pulsars are such obvious communication channels, why haven't we found any engineered signals? One possibility is that advanced civilizations avoid attracting attention, a galactic dark forest theory where broadcasting invites danger, or perhaps we're not listening correctly. Our algorithms are tuned to find natural pulsars, not deliberate patterns hidden within them. New machine learning tools are now scanning archival data for subtle irregularities, treating each pulsar like a locked safe waiting for the right combination. Whether pulsars are silent sentinels or interstellar telegraphs, their potential as cosmic messengers reshapes how we imagine contact. They remind us that communication might not come as a radio shout, but as a whisper woven into the fabric of the universe itself, a language written not in words, but in the precise, patient ticks of stellar timekeepers. And if we ever crack the code, the message waiting might not be "hello." It could be a library, a warning, or a eulogy for a civilization that once reached for the stars. When two neutron stars spiral toward each other in a death dance, they don't just collide, they detonate in a firestorm of creation. The resulting kilonova explosion unleashes energies so extreme, they warp the very rules of physics. In less than a second, tidal forces rip both stars apart, flinging neutron-rich material into space at relativistic speeds. What happens next is cosmic alchemy on steroids. The ejected matter, hotter than the sun's core and denser than an atomic nucleus, becomes a factory for heavy elements. Free neutrons bombard atomic seeds, building them up into gold, platinum, uranium elements so heavy ordinary stars could never forge them. The numbers are staggering. A single neutron star merger can produce hundreds of Earth masses worth of gold in moments. That's enough to coat every planet in the galaxy in a glittering layer. But these events aren't just about quantity, they're about precision. The R process, or rapid neutron capture, requires a perfect storm of conditions. Insane densities, blistering temperatures, and a flood of neutrons so intense, atomic nuclei can't stabilize before being hit again. Only neutron star collisions naturally create this environment. Supernova contribute too, but for the heaviest elements, kilonovae are the universe's primary foundries. We know this because the proof is literally all around us. The gold in your jewelry, the platinum in catalytic converters, even the uranium fueling nuclear reactors, they all bear the isotopic fingerprints of neutron star mergers. When scientists analyzed metal-rich stars in our galaxy, they found their heavy element ratios matched our process predictions perfectly. Even more convincing was GW 170817. The first neutron star collision detected via gravitational waves in 2017. Follow-up observations caught the infrared glow of newly minted heavy elements in the debris, a smoking gun confirming theories decades in the making. What makes kilonovae especially fascinating is their light show. Unlike supernova, which shine for weeks, kilonovae fade within days, but not before emitting a distinct reddish glow. This comes from lanthanides, rare earth elements whose complex atomic structures absorb and re-emit light in unique ways. Spotting this signature helps astronomers distinguish kilonovae from other cosmic explosions, even in distant galaxies. Some mergers might also produce short gamma-ray bursts, beams of high-energy radiation so focused, they're visible across the universe. If Earth lies in the path of such a beam, satellites detect it as a sudden flash, often the first clue that a neutron star collision occurred. Yet for all their brilliance, kilonovae are vanishingly rare. In our Milky Way, they might happen only once every 100,000 years. That's why every detected event is a treasure trove. By studying them, we're not just tracing the origins of precious metals, we're watching the universe's recycling program in action. Each collision scatters heavy elements into clouds that will eventually form new stars and planets. Our solar system likely contains gold from multiple mergers that occurred billions of years before the sun ignited. The implications stretch beyond astronomy. These events are natural laboratories for physics we can't replicate on Earth. The mergers warp space-time so severely, they allow us to test Einstein's theories under extreme gravity. The ejected matter, a mix of neutrons, protons, and quark-gluon plasma, offers glimpses into states of matter that haven't existed freely since the Big Bang. And the gravitational waves they produce, each ripple carries encrypted details about neutron stars' internal structure, data that could reveal whether their cores contain exotic particles or free quarks. So while gold might be the flashy headline, kilonovae's real gift is knowledge. They remind us that the cosmos doesn't just destroy, it transforms. Every neutron star collision is a cosmic reset button, scattering the ingredients for future worlds. And somewhere out there, another merger is brewing, waiting to seed the universe with stardust that might one day spark new life. Einstein's theory of relativity holds a mind-bending prediction. Mass doesn't just warp space, it stretches time itself. Near a neutron star or black hole, where gravity reaches unimaginable extremes, clocks don't tick the same way they do on Earth. Picture an astronaut in orbit around a pulsar, just a few dozen kilometers above its searing surface. For every hour they experience, years might pass back on Earth. This isn't hypothetical. GPS satellites orbiting our planet already account for tiny time shifts caused by Earth's gravity, adjusting their clocks by microseconds to stay accurate. But near a stellar remnant, the effect isn't subtle. It's a full-blown time warp where the universe's rulebook gets rewritten. The closer you get to one of these cosmic anomalies, the more extreme the time dilation becomes. Near the event horizon of a black hole, time slows to a crawl from an outsider's perspective. A single orbit might take mere seconds for the brave traveler, while centuries fly by for distant observers. This creates eerie scenarios straight out of science fiction. A spacecraft circling a black hole could return to Earth to find civilizations risen and fallen in its absence. Even neutron stars, though less extreme, distort time noticeably. Their intense gravity redshifts light escaping their surfaces, stretching wavelengths and slowing the apparent passage of time for anything near them. These distortions aren't just theoretical quirks, they're observable. When astronomers study pulsars, they account for gravitational time dilation to interpret their precisely timed flashes. Without correcting for relativity, the signals from a pulsar orbiting another dense object would drift out of sync, like a watch running slow in a strong gravitational field. These minute discrepancies allow scientists to map the invisible landscape of warped spacetime around stellar remnants, testing Einstein's predictions with celestial precision. The implications stretch far beyond keeping time. Time dilation near compact objects affects how we perceive their life cycles. A black hole's evaporation via Hawking radiation, for instance, appears frozen near its horizon. From our vantage point, the final moments of a dying black hole would seem to stretch into eternity, its last particles trickling out over epochs. Conversely, an observer falling in would experience their own time normally while watching the external universe speed up like a fast-forwarded film. This bizarre asymmetry isn't a flaw in the universe's design. It's a feature revealing how gravity and time are fundamentally intertwined. What makes these time-bending effects so valuable is how they serve as natural laboratories. By studying how light and matter behave in these extreme gravitational fields, we're probing the limits of known physics. Some theories suggest that at the quantum level near the Planck scale, time itself might become granular, a possibility that could reshape our understanding of reality. Stellar remnants, with their ability to stretch time to its breaking point, might be the key to unlocking these mysteries. They're not just relics of dead stars, they're clocks ticking at the edge of the unknown, each second holding clues to how the universe truly works. So the next time you check your watch, remember time isn't the constant we assume it to be. Out there in the cosmic deep, where stellar corpses warp the fabric of reality, it becomes fluid, malleable, and deeply strange. And in that strangeness lies a truth. The universe has far more ways to measure time than we've yet imagined. Deep within the heart of a neutron star, an invisible force rules with unimaginable power, a magnetic field so intense it could wipe a credit card clean from halfway across the solar system. These cosmic magnets aren't just strong, they defy comprehension, reaching strengths 1 trillion times greater than Earth's protective magnetic shield. Yet what's truly astonishing isn't their raw power, but their origin. These fields are relics, frozen in time during the star's catastrophic collapse, preserving a memory of the original star's magnetic personality, like a cosmic fingerprint pressed into the fabric of space itself. When a massive star exhausts its fuel and implodes, its core doesn't just shrink, it amplifies. Like a skater pulling their arms in to spin faster, the collapsing star concentrates its magnetic field into an infinitely denser space. This process, called flux conservation, takes a star that might have started with a magnetic field similar to the Sun's and turbocharges it into a monster. But here's the twist: not all neutron stars end up the same. Some, known as magnetars, possess fields so strong they occasionally crack under the strain, releasing bursts of gamma rays and X-rays visible across the galaxy. Others, like the calm millisecond pulsars, have weaker, but still formidable fields that guide their precise lighthouse beams. These differences aren't random, they're clues to how the original star lived and died. The real magic happens when scientists decode these magnetic messages. By measuring how a pulsar's beams slow down over time, a phenomenon called spin-down astronomers can calculate the strength of its magnetic field. This isn't just textbook physics, it's stellar archaeology. A neutron star with an ultra-strong field might have been born from a rapidly rotating progenitor, its magnetic lines twisted and amplified by internal dynamos before collapse. A quieter field could hint at a star that shed magnetic energy in violent stellar winds before its final demise. Even the orientation of these fields tells a story. Some pulsars beam radiation directly along their magnetic poles, while others wobble like a spinning top, their misaligned fields revealing ancient asymmetries in the supernova explosion that birthed them. These invisible forces don't just shape neutron stars, they transform their surroundings. Magnetars, for instance, can generate starquakes, where their crusts fracture under magnetic stress, releasing energy equivalent to a solar flare packed into a sphere barely 20 kilometers wide. The resulting disturbances ripple through surrounding nebulae, accelerating particles to near light speed and lighting up gas clouds like neon signs. The Crab Nebula's eerie glow, that's largely powered by its central pulsar's magnetic field, which acts like a cosmic power plant, converting rotational energy into radiation and particle winds. But the most tantalizing possibility lies in how these fields preserve information. Just as tree rings record Earth's climate history, A neutron star's magnetic field might encode details about the turbulent plasma dynamics of its parent star's core, conditions we could never observe directly. Some theories even suggest that exotic quantum processes in the star's interior, like the alignment of neutron spins, could leave subtle imprints on the external magnetic field. Unlocking these signals would be like finding a stellar diary written in the language of magnetism and waiting centuries for readers. So while black holes might steal headlines with their gravity, neutron stars whisper their secrets through magnetism. Every flicker in their beams, every crack in their crusts, every ripple in their surrounding nebulae is a line in a much larger story, one that stretches back to the star's birth and forward to its eventual decay. And as we learn to interpret these invisible forces, we're not just studying dead stars, we're learning to read the universe's hidden ledger, where magnetism is the ink and neutron stars are the pages. White dwarfs are the universe's silent archivists, no violent explosions, no crushing gravity wells, just a slow, dignified fade into darkness. These stellar embers, no larger than Earth yet packing half the mass of our Sun, represent the fate awaiting 97% of all stars, including our own. When a Sun-like star exhausts its nuclear fuel, it doesn't go out with a bang. Instead, it gently puffs away its outer layers, leaving behind a glowing core so dense that a teaspoon of its material would weigh as much as an elephant. But don't let their peaceful demise fool you. These cosmic diamonds hold just as many secrets as their flashy neutron star cousins. They simply whisper them across eons rather than screaming into the void. What makes white dwarfs exceptional time capsules is their pristine composition. Unlike the chaotic aftermath of supernova, where elements get scrambled beyond recognition, a white dwarf's interior remains a neatly layered record of its former life. Imagine slicing through one. You'd find oxygen and carbon dominating the core, remnants of the star's final fusion stages, surrounded by a thin shell of helium and an even thinner veneer of hydrogen, like the rings of a celestial tree trunk. These layers aren't just leftovers, they're chemical diaries, documenting every fusion reaction that powered the star for billions of years. By studying their light spectra, astronomers can read these diaries line by line, reconstructing not only how the star lived but also the composition of the nebula that birthed it. Take Sirius B, the closest known white dwarf. Its atmosphere, stripped of hydrogen by violent interactions with its brighter companion, reveals a surface dominated by helium, a clue that it once burned hotter and faster than our Sun. Contrast this with the white dwarf H1504+65, whose oxygen-rich atmosphere suggests it was once a massive star that violently ejected its outer layers before collapse. Each of these quiet relics tells a different story, their surfaces acting like cosmic black boxes preserving data from stellar lives that ended long before Earth formed. Perhaps most remarkably, white dwarfs preserve evidence of their planetary systems. As they cool, their intense gravity pulls in debris from surrounding asteroids and comets, polluting their otherwise pure atmospheres with traces of rock-forming elements like silicon, magnesium, and iron. The white dwarf G29-38, for example, bears spectral signatures of vaporized asteroids in its atmosphere, telltale signs that it once hosted planets now reduced to dust. This phenomenon turns aging white dwarfs into cosmic archaeologists, their atmospheres cataloging the remains of alien solar systems. Some even show evidence of water-rich asteroids, hinting that distant planetary systems may have harbored oceans similar to ours. Our own Sun will one day join this quiet cosmic graveyard, 5 billion years from now, after swelling into a red giant that engulfs Mercury and Venus. it will shed its outer layers into a beautiful planetary nebula, leaving behind a white dwarf that will glow faintly for trillions of years. Unlike neutron stars or black holes, these remnants don't vanish, they simply cool, becoming black dwarfs so cold they'd be invisible against the cosmic background. None exist yet, the universe isn't old enough, but when they finally form, they'll be the ultimate time capsules, preserving information in their crystalline cores long after every other stellar remnant has faded away. So while white dwarfs may lack the drama of supernova or the mystery of black holes, their patient endurance makes them ideal cosmic historians. They remind us that not all stellar deaths are cataclysmic. Some are gentle transitions, where the universe carefully packs away its memories in diamond-like vaults, waiting for curious minds to decode them. And as we study their fading light, we're not just learning about dead stars. We're glimpsing the quiet destiny awaiting our own sun, and the unimaginable future of a universe where these dim embers may be the last visible reminders that stars ever shone at all. The sun's golden glow won't last forever. Beneath its steady warmth lies a ticking clock. In roughly 5 billion years, the hydrogen fuel powering its core will finally run dry, triggering a chain of events that will transform our familiar star into something entirely different. Unlike massive stars that go out in supernova explosions, the sun's death will be a slower, more methodical affair. As its core contracts, the outer layers will swell into a red giant, engulfing Mercury and Venus and baking Earth's surface to a crisp. But the real metamorphosis comes later, when those bloated outer layers drift away into space, leaving behind a white dwarf, a dense, Earth-sized ember that will glow faintly for trillions of years. This stellar afterlife might lack the fireworks of a supernova, but it's no less significant. White dwarfs are cosmic archivists, their compositions preserving detailed records of their former lives. The sun's remnant will crystallize into a lattice of carbon and oxygen, a crystalline tombstone etched with the history of its nuclear fusion processes. Future civilizations, or whatever intelligence arises in the distant cosmos, could analyze its light to determine how much helium it fused, how quickly it burned, even the composition of the primordial cloud that birthed it. Every element in its atmosphere, every trace of heavier metals, would tell a story about the solar system that once orbited it. What's especially haunting is how long this remnant will endure. White dwarfs cool so slowly that not a single one in the universe has yet faded to complete darkness. The cosmos simply hasn't existed long enough. The sun's white dwarf phase will outlast every galaxy, every black hole, even the decay of protons themselves, if current theories hold. It will become one of the last sources of light in an increasingly cold and empty universe, a final whisper of the era when stars like ours shone brightly. Yet even in death, the sun won't be alone. Its gravitational pull will linger, anchoring the ruins of our solar system. Planets that escaped vaporization, perhaps Jupiter or Saturn, will continue their orbits in the darkness, now circling a dim, dense relic rather than a vibrant star. Asteroid belts and cometary debris, frozen and silent, will remain as a fossilized record of the system's architecture. And if any human artifacts survive, whether Voyager probes or geological strata, they'll rest in the shadow of a star that once nurtured life, now reduced to a fading cinder. The lesson here isn't just about our sun, it's about the universe's quiet persistence. Every star, no matter how humble, leaves something behind. A white dwarf, a neutron star, a black hole. Each is a time capsule, encoding the physics of its birth and the conditions of its demise. For civilizations that learn to read these relics, the cosmos becomes an open book, its pages written in the language of gravity, light, and elemental dust. And long after our sun's light winks out, its remnant will still whisper secrets to anyone who knows how to listen. Exoplanets circling dead stars defy everything we know about cosmic survival. Imagine a world locked in orbit around a pulsar, bathed not in gentle sunlight, but in deadly X-rays and gravitational tides powerful enough to shred continents. Yet these zombie planets not only exist, they thrive in conditions that would vaporize Earth in seconds. The first such planet ever discovered, PSRB 1257+12b, orbits a millisecond pulsar that blasts it with radiation thousands of times stronger than our Sun emits. This isn't science fiction, it's proof that planetary systems can outlast their stars' violent deaths and adapt to environments we once thought impossible for survival. The survival mechanisms of these worlds read like a masterclass in cosmic resilience. Take white dwarf systems, where surviving gas giants often orbit closer than Mercury does to our Sun. When their host star swelled into a red giant, these planets should have been swallowed whole. Instead, many migrated inward, riding waves of gravitational interaction as their dying star shed mass. Others might be second-generation worlds reformed from the debris disks of shattered planets after the star's collapse. The white dwarf WD 1145+017 even sports a dust ring with clear signs of planet formation, suggesting that in some systems, the process of creating new worlds begins anew even after stellar death. What makes these survivors so valuable isn't just their toughness, it's the window they provide into our own planet's ultimate fate. As our Sun ages, it will follow the same path as these white dwarfs, leaving Earth to face an impossible choice: either get pushed outward as the Sun loses mass, risking orbital instability, or get dragged inward and vaporized. Studying how exoplanets navigate this stellar metamorphosis helps model potential escape routes, perhaps through gravitational assists from Jupiter or strategic orbital adjustments. The fact that planets persist around 1 in 3 white dwarfs we've observed offers cautious hope that some form of our solar system might endure. Even more intriguing are the possibilities for life in these extreme environments. While neutron star planets face deadly radiation, tidal heating could maintain subsurface oceans on their moons similar to Jupiter's Europa, but powered by gravitational kneading rather than sunlight. Around white dwarfs, a planet orbiting at the right distance could enjoy billions of years of stable warmth as the remnant slowly cools. Calculations show such a world might even retain an atmosphere if it migrated there after the star's violent red giant phase. The dim red glow of an aging white dwarf could provide just enough energy for photosynthetic life to cling on, turning these systems into unlikely oases in the stellar graveyard. The ultimate surprise comes from how these systems challenge our definitions of habitability. On Earth, we assume life needs a sun-like star, but zombie planets prove that biological processes might persist under pulsar beams or white dwarf embers. Some extremophile microorganisms on Earth survive intense radiation by living deep underground or producing protective pigments. Similar adaptations could theoretically evolve on planets orbiting stellar remnants, rewriting the rules for where we search for extraterrestrial life. Future telescopes might even detect biosignatures in the atmospheres of these worlds, revealing that life can emerge not just in a star's prime, but in its afterlife. So while Hollywood paints stellar death as the ultimate apocalypse, the universe keeps proving it's more like a phase change, a transformation where old systems break down, but clever survivors adapt and new possibilities emerge. These zombie planets aren't just curiosities, they're pioneers, showing us that cosmic real estate remains valuable long after the lights go out. And as we discover more of them, we're not just mapping exotic worlds, we're glimpsing potential pathways for survival in the unimaginably distant future when our own sun joins the ranks of the stellar undead. Dark energy is the universe's greatest unsolved mystery, an invisible force stretching space itself apart at an ever-increasing pace. Yet for something so powerful, it leaves almost no trace. No light, no particles, no direct signals, but there's a surprising place we might find its fingerprints, in the slow, steady spins of dead stars. Neutron stars, those ultra-dense relics of supernova explosions, could be acting as cosmic seismometers, their rotations subtly influenced by dark energy's relentless push. Imagine these stellar corpses as precision instruments scattered across the galaxy, each one a silent witness to the universe's accelerating expansion. The connection lies in the fabric of space-time itself. As dark energy stretches the universe, it doesn't just move galaxies apart, it alters the very geometry of space on microscopic scales. Over centuries, these infinitesimal changes could accumulate, affecting how neutron stars spin. Their rotations are already astonishingly stable, rivaling atomic clocks. But if dark energy's influence varies over time or interacts differently with ultra-dense matter, it might introduce tiny deviations in their spin rates, changes so slight they'd take decades of observation to detect. Pulsars, which beam radiation like cosmic lighthouses, are ideal for this detective work. Their regular pulses serve as a natural clock, and any unexpected shifts could hint at dark energy's hidden mechanisms. One tantalizing theory suggests that dark energy isn't constant but evolves, growing stronger or weaker over cosmic time. If true, neutron stars in different galactic neighborhoods, some in crowded regions, others in near-empty voids, might show contrasting spin behaviors. By mapping these variations, astronomers could reconstruct dark energy's history, tracing how its influence has changed since the first stars died. It's like using stellar gravestones to read the universe's expansion diary. The stakes couldn't be higher. Dark energy doesn't just shape the universe's fate, it dominates it, making up nearly 70% of all the energy in existence. If it continues accelerating expansion unchecked, the cosmos could face a big rip, where galaxies, stars, and even atoms are torn apart. Alternatively, dark energy might weaken, allowing gravity to eventually reverse the expansion in a big crunch. Neutron stars, with their billion-year lifespans, are uniquely positioned to help forecast these outcomes. Their spins could reveal whether dark energy is truly static or a dynamic force with surprises still in store. Already, projects like the International Pulsar Timing Array are laying the groundwork for this research. By linking radio telescopes across continents, they monitor dozens of pulsars with nanosecond precision, searching for patterns that might betray dark energy's hand. Future observatories like the Square Kilometre Array will extend this network, turning the galaxy into a vast dark energy detector. Each pulsar becomes a data point in an experiment spanning light years, where the universe itself is both the lab and the mystery to be solved. So while dark energy remains invisible, its shadow may flicker in the ticking of dead stars. Every rotation, every pulse, every subtle slowdown carries a message not just about the stars themselves, but about the invisible force shaping everything. And as we listen to these cosmic timekeepers, we're not just studying stellar remnants, we're decoding the fate of the universe one spin at a time. For centuries, astronomy meant one thing: studying light. Telescopes collected photons from distant stars, and that was our only window into the cosmos. But the universe communicates in more ways than just light. It sends whispers through space-time, ghostly particles, and high-energy bullets of matter. Now, for the first time in history, we're learning to listen to all these cosmic messengers at once. This is Multimessenger astronomy, and it's revolutionizing how we decode the stories of dead stars. Take the groundbreaking event in August 2017. For decades, physicists had predicted that colliding neutron stars would ripple spacetime with gravitational waves while simultaneously flooding the cosmos with gamma rays. But no one had ever caught both signals from the same event until LIGO detectors felt the spacetime tremor, and 2 seconds later, NASA's Fermi satellite spotted a gamma ray flash from the same patch of sky. Suddenly, theories became reality. This wasn't just an observation. It was the universe handing us a Rosetta Stone, translating between gravitational and electromagnetic languages. The magic lies in how each messenger reveals different secrets. Gravitational waves, born from massive objects warping spacetime, tell us about the dance of merging neutron stars, their masses, spins, and how they distorted just before collision. Neutrinos, those nearly massless particles that streak through planets unimpeded, carry news from a supernova's heart where light gets trapped. Cosmic rays, atomic nuclei accelerated to near light speed, map the shockwaves racing through stellar debris. And traditional light, from radio waves to X-rays, paints the aftermath in vivid detail, showing us where heavy elements like gold are forged. Combining these signals creates something greater than the sum of its parts. When the neutron star merger GW170817 lit up detectors, astronomers didn't just confirm heavy element production, they measured it. The gravitational waves revealed the collision's energy, while the kilonova's infrared glow showed how much gold was created. Together, they proved in one stroke what decades of theory had suggested. Neutron-star collisions are cosmic alchemy labs where the universe forges its most precious elements. This approach is also solving long-standing mysteries. For years, some supernovae seemed oddly lopsided, their explosions ejecting material unevenly. Then in 2018, neutrino detectors caught particles from supernova 1987, arriving slightly ahead of the light, proof that the core collapsed asymmetrically, sending neutrinos flying in one direction while the shockwaves struggled outward. Without multimessenger data, we'd never have known that stars don't just die, they die with a stagger, like falling trees caught mid-collapse. The future is even more thrilling. Imagine catching a supernova's neutrino burst hours before the visible explosion, giving telescopes time to aim, or tracing a cosmic ray back to a pulsar's violent particle jet using gravitational wave timing. Somewhere out there, a black hole swallowing a neutron star might be emitting all 4 messengers at once: gravitational waves, neutrinos, gamma rays, and cosmic rays, a cosmic symphony waiting for our detectors to harmonize. What makes this era so transformative isn't just new technology, it's a fundamental shift in how we see the universe. We're no longer passive observers staring at flickering lights. We're active listeners tuning into a cosmic conversation that's been ongoing for billions of years, learning to hear the full story written in gravity, particles, and radiation. And with every multimessenger event, we're not just studying dead stars, we're learning to speak their language. Simulating the violent death of a star isn't just about running equations, it's about reconstructing cosmic chaos atom by atom inside supercomputers. Modern astrophysics has reached a point where we can take all the known laws of physics, fluid dynamics, nuclear reactions, magnetic fields, gravity, and compress them into digital laboratories that recreate stellar collapses with breathtaking precision. These aren't simple animations, they're trillion-particle virtual experiments where every electron, proton, and neutrino plays its part in the unfolding catastrophe. One such simulation, run on Oak Ridge National Laboratories' Frontier supercomputer, tracked over 60 billion computational elements as they mimicked the final milliseconds of a massive star's life. The result, a shock wave that stalled, just as real supernova observations suggest, before reigniting in a violent rebound that blew the star apart. A detail telescopes could never catch, but simulations revealed in pixel-perfect detail. What makes these digital recreations so revolutionary is how they expose hidden physics. In nature, a supernova's core is buried under layers of stellar material, invisible to our telescopes. But simulations peel back the curtain, showing how neutrinos, those ghostly particles that barely interact with matter, actually carry away 99% of the explosion's energy, leaving just enough to power the shockwave that rips the star apart. They've revealed bizarre phenomena like neutrino-driven convection, where these particles heat pockets of gas that then rise like bubbles in a boiling pot, helping reignite the stalled shock. Without simulations, we'd have no way to see these intricate mechanisms that determine whether a star dies with a whimper or a universe-shaking bang. The real magic happens when virtual meets observational. When the LIGO gravitational wave detector caught the ripple from two neutron stars colliding in 2017, supercomputer models had already predicted what such an event should look like. The actual data matched simulations so closely that researchers could immediately identify the telltale signatures of heavy element creation in the aftermath. This synergy is transforming how we interpret stellar remnants, like having a Rosetta Stone that translates between computer code and cosmic phenomena. Discrepancies between models and reality aren't failures. They're treasure maps pointing to gaps in our understanding, whether it's the true nature of matter at neutron star densities or how magnetic fields twist during collapse. Perhaps most astonishing are the emergent behaviors no one predicted. Some supernova simulations spontaneously develop lopsided explosions, solving the mystery of why many stellar remnants shoot through space at incredible speeds. Others show neutron stars being born with mountains, tiny imperfections on their surfaces no taller than a pencil, yet dense enough to distort spacetime and emit gravitational waves. There's even speculation that certain ultra-precise pulsar glitches might be caused by starquakes in these crystalline crusts, a phenomenon first glimpsed in simulations before being hunted in real data. As supercomputers grow more powerful, the line between simulation and observation blurs further. Next-generation models will incorporate quantum chromodynamics to probe neutron star cores, general relativity to track spacetime warps around collapsing stars, and even dark matter interactions that might alter stellar life cycles. Each advance turns these digital experiments into time machines, letting us rewind cosmic catastrophes frame by frame to read the universe's hidden scripts. The stellar corpses we study aren't just in points, they're complex systems with stories to tell. And thanks to simulations, we're finally learning their language. Ethics rarely come to mind when we gaze at the stars until you realize we're not just observers anymore. With telescopes powerful enough to decode the spin of neutron stars and simulations that reconstruct stellar deaths atom by atom, humanity has crossed a threshold. We're no longer just studying cosmic time capsules, we're learning to manipulate them. Imagine a future where we harness pulsar beams as interstellar navigation tools or extract heavy elements from kilonova debris fields. The technology isn't fantasy. Scientists have already proposed using neutron stars' precise pulses as galactic GPS, but every intervention carries risks. Tweaking a pulsar's magnetic field could unintentionally redirect its deadly radiation toward inhabited systems, like swinging a lighthouse beam toward a coastline. The black hole information paradox presents an even thornier dilemma. If we ever crack the code to retrieve data from an event horizon, would we be opening Pandora's box? Theoretical physicist Stephen Hawking warned that black holes might not just store information, they could transform it. Attempting to decode what's inside could release scrambled quantum states with unpredictable effects, like trying to play a DVD melted in a furnace. Some models even suggest that extracting information might destabilize the black hole's structure, triggering miniature eruptions of Hawking radiation. While these scenarios sound like science fiction, they force us to confront a sobering truth. Stellar remnants aren't inert museum pieces. They're active, dynamic systems that obey laws we're still deciphering. These debates echo terrestrial ethical quandaries in surprising ways. The rush to mine asteroids for rare metals mirrors proposals to harvest neutron star material for ultra-dense construction. But just as strip mining Earth has consequences, extracting matter from stellar corpses could disrupt delicate gravitational balances in star clusters. Even passive observation raises questions. When we study the light from ancient supernova, we're essentially reading the universe's diary without consent. Indigenous cultures have long emphasized sacred relationships with celestial bodies. As our tools grow more intrusive, we risk repeating colonial patterns of exploitation on a galactic scale. Yet the most profound responsibility lies in how we share these discoveries. Stellar archaeology reveals that every atom in our bodies traces back to dead stars, a truth that could unite humanity as heirs to cosmic legacy or deepen divisions if access to celestial resources becomes unequal. The same pulsar timing arrays that test general relativity could also be weaponized as precision guidance systems for interstellar missiles. Knowledge from stellar remnants doesn't come with an instruction manual. We write the rules as we go. Perhaps the lesson lies in how these cosmic relics themselves behave. Neutron stars don't hoard their energy. They beam it across galaxies as lighthouses for wayfarers. Supernova scatter their elements freely, seeding future worlds. As we learn to read the universe's time capsules, their greatest gift might not be the secrets they reveal, but the model they offer. That preservation and generosity aren't opposites, but two rhythms in the same cosmic heartbeat. Our challenge isn't just unlocking stellar mysteries, it's ensuring that in doing so, we honor the same balance that crafted these celestial archives over billions of years. Public engagement with cosmic mysteries. Stellar remnants captivate the public, inspiring art, music, and storytelling. Museums and planetariums use supernova visuals to spark curiosity, while citizen science projects let amateurs help analyze pulsar data. By sharing these cosmic wonders, scientists foster a deeper connection between humanity and the universe. Collapsing stars aren't just scientific tools, they're cultural touchstones. Few cosmic phenomena ignite the imagination like the death throes of stars. When the Hubble Space Telescope captured the Crab Nebula's swirling filaments, or when Chandra revealed the haunting X-ray glow of Cassiopeia A, those images didn't just fill scientific journals, they became cultural icons. The vibrant hues of supernova remnants have graced album covers, from Pink Floyd's Dark Side of the Moon to Beyoncé's cosmic visuals. Composers like John Adams have translated pulsar rhythms into symphonic movements, turning the precise ticks of neutron stars into auditory art. Even fashion designers riff on stellar palettes, with runway collections mirroring the golds and blues of kilonova debris. These creative interpretations aren't just homage, they're proof that stellar death resonates as deeply as birth, weaving science into the fabric of human expression. Planetariums have long been gateways to these cosmic wonders, but today's technology takes immersion further. The American Museum of Natural History's Worlds Beyond Earth show wraps audiences in 3D supernova explosions, letting them stand inside the shockwaves that sculpt nebulae. Meanwhile, virtual reality experiences like Neutron Star Explorer allow users to touch a pulsar's magnetic field or witness a black hole's gravitational lensing firsthand. These aren't just spectacles, they're empathy machines, helping people grasp extremes of density and gravity that defy earthly comparison. When a child reaches out to catch a virtual neutron star fragment, only to see it weigh millions of tons in their hand, abstract physics becomes visceral. Citizen science bridges the gap between awe and participation. Projects like Einstein at Home harness idle computing power from volunteers worldwide to sift through gravitational wave data, leading to discoveries like the Pulsar J 2007 plus 2722, a lone neutron star spinning without a companion, found by a German engineer's home computer. On Zooniverse's Radio Galaxy Zoo, amateur astronomers help classify jets from black holes and neutron stars, contributing to real research. These initiatives democratize cosmic exploration, proving you don't need a PhD to advance our understanding of stellar remnants. The storytelling around these phenomena matters just as much as the science. When Chilean astronomers shared the pale blue dot image from Voyager, framed by light scattered from a long-dead star, it wasn't just astronomy, it was poetry. Podcasts like Star Talk translate neutron star physics into cocktail party conversations, while YouTube creators use sandbox simulations to let viewers play with supernova. This cultural dialogue transforms stellar corpses from distant curiosities into shared touchstones, reminding us that the iron in our blood and the gold on our fingers were forged in the same cataclysms we study. By making stellar remnants relatable, scientists and artists together answer a profound human need to see our stories reflected in the cosmos. Whether through a musician's ode to a pulsar's beat or a child's wonder at a planetarium show, these connections reveal a truth deeper than equations. We're not just observers of the universe. We're its conscious witnesses, inheritors of stardust, and storytellers for the ages yet to come. Collapsing stars are the universe's librarians, meticulously preserving records in ways we're only beginning to decipher. These cosmic remnants don't just mark the end of a star's life, they're active participants in the story of everything, holding onto clues about how galaxies form, how matter behaves under extremes, and even how the building blocks of life itself came to exist. Take neutron stars, for example. Their unimaginable density locks away secrets about the fundamental nature of matter, while their precise pulsations serve as celestial metronomes, keeping time across the eons. Black holes, often seen as the ultimate cosmic erasers, might actually be the most secure vaults of all, encoding information in the ripples of their event horizons like data etched into quantum stone. What's truly humbling is how these stellar relics connect directly to us. Every heavy atom in your body, the iron in your blood, the calcium in your bones, was forged in the heart of a dying star and scattered across space by supernova explosions or neutron star collisions. We're not just observers of these processes, we're products of them. The gold in a wedding ring, the uranium powering cities, even the silicon in your smartphone, they all trace back to the violent deaths of stars that shone long before Earth existed. These elements don't just tell the story of the cosmos, they tell our story, written in the language of atomic nuclei. But the significance of stellar remnants goes beyond chemistry. They're natural laboratories for physics we can't replicate on Earth. When neutron stars merge, they warp space-time so severely that the gravitational waves they produce let us test Einstein's theories under conditions a billion times more extreme than anything in our solar system. White dwarfs cooling slowly over trillions of years preserve layered records of stellar nucleosynthesis like tree rings frozen in time. Even the faintest pulsar glitch, a tiny hiccup in rotation, can reveal details about the superfluid dynamics deep inside these ultra-dense objects, offering glimpses into states of matter that defy imagination. The beauty of studying these cosmic time capsules is that they're everywhere. The Crab Nebula's wispy filaments, the ghostly X-ray glow of Cassiopeia A, even the invisible gravitational echoes of black hole collisions. Each one is a page in a universal archive waiting to be read. And with every advance in technology, from gravitational wave detectors to space telescopes, we're learning to decode more of their secrets. What might we discover next? Perhaps evidence of exotic particles lurking in neutron star cores, or new clues about dark matter's influence on stellar evolution. Maybe even answers to existential questions about the universe's ultimate fate. So when you step outside on a clear night and gaze up, remember, some of those points of light aren't just stars. They're messengers from the distant past, carrying stories of cosmic alchemy, gravitational drama, and the unbreakable chain that links the universe's grandest scales to the smallest particles. And as we continue to unravel their mysteries, we're not just exploring space, we're uncovering our own origins. If this journey through the cosmos has sparked your curiosity, join the conversation below. Share your thoughts, questions, or even your favorite stellar remnant, because the universe's greatest stories are still being written, and every one of us gets to be part of the next chapter. Don't forget to like and subscribe for more deep dives into the wonders of space. The night sky is full of secrets, and together we'll keep decoding them one starlit